Is 1:33, and I'll call our commission workshop to order. All commissioners are present. If we could do introductions, and we'll go around the room. We'll start with you this time, Lisa.
Lisa Middlestar, Executive Director for the Morrow.
Joe Little, Parametrics.
Chad Snyder for Morrow.
Jacob King, I'm sorry.
Debbie Rady, Board of Foods.
Jacob King, Port of Morrow.
Jason Hendricks, Port of Morrow.
Port of Morrow.
Nick Growy, Aqua Engineering.
Cody Glauber, Aqua Engineering.
Bob Frashetti, Aqua Engineering.
Okay, yeah.
Online, you have, Gary Conklin.
And
Yep.
I think, just because there's so many, how about you just read out the names, or we okay just to see them up there?
They recorded all their names on there, so I mean,
Okay.
we don't have to call them out.
I don't think we need to go through everybody unless there's somebody specific.
The only one that could be multiples is Morrow County Planning.
Hi, this is Tamara from Morrow County Planning.
Okay.
There you go. I don't see any others that would.
The board's okay not announcing those, going through that? Okay. All right, we're good. Well, we'll move on to our item number 2, secondary treatment discussion. Lisa, I'll turn this over to you or Mark. Oh, I probably easy, but.
We're gonna turn it over to Jacob.
Yes, we are.
Thanks, guys.
If you don't like it, take my fault.
It's always my fault.
So based on our last conversation on secondary treatment, we went back kind of to the drawing board, start looking at alternate options due to, as you guys are well aware, the high cost of the last approach. So with me today is a team from Aqua Engineering. Aqua's been working with the board going on 2 years. They were our primary designer and project manager for the 2 large wastewater lagoons that we're currently under construction on now. So Nick's been our point of contact for going on 2 years, and when this came around, I engaged Nick and said that this is perfect for Aqua's previous background, and they were up for the job. So so here's, I'll let them introduce themselves, and we'll go from there. Thanks, Jake. We're gonna go ahead and pull a little slide deck here. Then can you do, are we sharing?
It should just work.
Okay.
Is it green on the bottom and that's something when you want to. Or do the whole computer. Sorry. Oh, no. Here we go. Presentation or the focus.
Thanks, man.
Okay.
Go more. Yeah, great, thank you. All right, thanks for the intro, Jake. I'm Nick Growy, Aqua Engineering. I'm from our Beaverton, Oregon office, just a few hours west of here. As Jacob mentioned, I've been working for the port for about 2 years now. We helped with the design, permitting, and now we are managing the construction of your guys' 1.6 billion gallon water storage project. It's been a great success so far. We've done a wonderful contractor. That project is going smooth. As Jake mentioned, he recently asked us for our assistance in evaluating a secondary treatment system for your industrial wastewater system. So I've brought my colleagues with me here. I've got Cody Vavra and Bob Frashetti. Cody's a chemical engineer with Aqua. Bob Frashetti is a senior principal. Both of these guys are out of our Colorado office, and I will let them introduce themselves in just a little bit here. Go to the next slide. There. Okay, just to kind of briefly cover our main topics of discussion. We're gonna go over the project as a whole. I know many of you are familiar with the project, but we're gonna kind of reaffirm our understanding of it, let you guys ask some questions. we'll go over, our understanding of the basis of design, that is kind of the details of how the project would work, the constituents that we're trying to remove. Item number 4, we have come up with a conceptual treatment system. We're gonna go over that, what it looks like, how it's sized, how we came up with the recommended system. Finally, we'll cover opinion of construction costs. Again, this is all very conceptual level. This is about 4 or 5 weeks of work that you're seeing here, so this is a bit of a longer term design than that, but at this point, we feel comfortable to present this information to you, as we do feel confident about what we found. And finally, we'll close out with some discussion. I'm sure many of you have questions about where we are at and where we are going. So we encourage some new discussion. So with that, I'm gonna hand the torch over to Bob. Again, I'm head of our Beaverton, Oregon office, Aqua Engineering. We've got offices in Oregon, Colorado, and Utah. Bob is our senior principal that manages our Colorado team. And I'll let him introduce himself and talk about his background.
Thank you for having us. So in addition to the civil engineering work that we do with you guys, we also have a very strong process, wastewater, engineering, electrical controls, and instrumentation team. In fact, I would say that's our primary service area. We've been doing wastewater facility design since the 90s. I started in engineering in 1990. I've been with Aqua for the last 8 years. I was an engineering company prior to joining Aqua. And through interesting path, ended up being a principal at Aqua as well. So Aqua is about 80 people, process engineers, chemical, process engineers, electrical, civil. So this is what we do is wastewater treatment. We specifically focus, I would say in the last 10 to 15 years, more and more on nitrogen control, what we call DNR, which is biological nutrient removal. And we're super excited to help you guys solve this challenge with your nitrogen. As I mentioned, we're about 80 people, sprinkled between 3 offices in the West. Cody, you shouldn't escape being introduced. So go ahead, Cody.
I'm Cody Barbara, Aqua Engineering. I'm a chemical engineer. My background is more industrial. I started in the ethanol industry, process engineering, production management. Then moved into Aqua about 6 years ago, kind of lead our industrial division, water recovery, for brine disposal, wastewater treatment. So I'm very familiar with industrial wastewater.
All right, I'll take the project overview here. So, what we understand is we're talking about a secondary treatment system for, the port's industrial wastewater collection and treatment system. We currently have an effluent, leaving the anaerobic digester system, the existing anaerobic digesters that were recently installed and commissioned. The water that is leaving those digesters has a nitrogen content of roughly 110 milligrams per liter. What we've been asked to do is evaluate a system that will be able to reduce that 110 down to a number that is near 40 milligrams per liter, with the potential to actually be able to adjust that amount depending on what the farmers may be needing on the back end during the growing season. In addition to the nitrogen reduction aspect of the project, we do need to be aware of biological oxygen demand, or BOD, as well as total suspended solids, or TSS is what we call that. Got a question?
Yeah, your comment earlier, in the first line, adjusting it to what the farmers might need, that's adjusting it up, right?
That's correct.
Not
Yeah,
down.
we would assume that adjustment would be north of that 40 number.
Okay.
Correct. So BOD and TSS are both 2 parameters that we need to keep a close eye on, because during the winter season, when this water is being stored in these very large and very deep lagoons, both of those 2 parameters will absolutely contribute to odor. So we need to keep those numbers down to keep the odor at a good level. Finally, we've been designing this around a sequencing batch reactor system, also known as a SBR. This was actually suggested to us by Jake and his team. We really like the idea. We're big fans of SBRs, so we're using that as a concept. In addition to utilizing earthen lagoons rather than big concrete structures. We're planning on, essentially digging holes in the ground, lining those holes with HDPE liner. That will tremendously save on costs as compared to concrete basins, which we'll get into a little bit further. And then finally, we're gonna close out with a planning hole cost estimate that we have today.
So milligrams per liter, is that synonymous with parts per million?
Yes, correct.
So what would that be, what would that equate to roughly like in pounds of nitrogen per inch of water?
That's a good question. I might ask, can we make that to let's see quickly?
Yeah, I can, it is,
Yeah.
off the top of my head.
It's a calculation to get to that answer, but yes, we could. Yeah, you could.
I know the answer, I mean.
To convert milligrams per liter to pounds per day, you take the concentration multiplied by the flow in MGD times 8.34. And that'll give you pounds per day of whatever that group was. And so we have a basis of design where we look at that, because you're right, we have to look at the mass balance as well as the concentrations.
We're talking somewhere between 10 and 20.
Yeah, I think for the 90 milligrams per liter, the port, it's around 22 to 24 pounds of nitrogen. So if you take it down to 40, you're probably have that. So
I just wanted to give reference on what we're talking.
Cody, you wanna talk about our basis of design?
Yeah, so characterizing influent wastewaters is the most important part as we start this project, just so we understand really what are the nuances of this specific flow that we're treating, with the collection system that the port has, just to characterize, from food processor, power plant, the data centers. We look at the flow, so how is it coming into us, what are we gonna be treating on the pollutant side, the organics, the suspended solids, nitrogen. We need to look at the environmental conditions, so where are we at geographically, elevation, we're looking at relative humidity, temperature ranges, what type of temperatures do we see in the process, and also the geotechnical considerations, because earthen lagoons, will rely heavily on the geotechnical analysis for geotextile grids and how the lagoons are constructed and what is the constructability concerns as it relates to those. Groundwater is also considered, because that's something that could be a big cost if we have to dewater, and may limit sometimes if you go too deep and you're hitting groundwater, how deep you want to go with your basin design. It's not a concern at this site, but it is something that we consider. Then the design takes a look at the effluent targets, so what are we trying to target in the effluent to minimize odor, suspended salt buildup in those effluent lagoons, and then the nitrogen going out in the water. So here what we did was, this first column here characterizes the current wastewater, characterizes the current wastewater flows and loads across the flow, organic loading, suspended solids, and nitrogen. So what we did is we worked with Jacob before, and we then used that information to size the facility based on a future flow of up to 13 million gallons per day. So that's about a 35 to 40% increase in what the flows they're currently seeing, that allows for expansion, that allows for a train brought offline for servicing the equipment, and still being able to meet the current target of the 40 TN goal. So right now, there's really no effluent targets in the current facility, and then we have established the new criteria for that for this new design. We've also corrected the influent temperature, pH, the ambient temperature conditions, site elevation, groundwater, and then the soil description for the area being the loamy pine sand.
When you say not expected on the groundwater, you mean not expected to meet groundwater
In the excavation
in the
depth of,
elevation of the infrastructure?
correct, yeah.
We found groundwater around 50 feet deep, from the existing grade, and we're well above that with our current design.
So here's just an overview of the existing treatment site currently, so here the influent comes in. Splits to these three anaerobic lagoons, and then that effluent then goes into this holding pond and distributed out for irrigation. Our treatment site generally is in this area down here in the southwest corner, that is beneficial to the hydraulics of the site, because it's the lower point on the site, and so our evaluation was a concept level, taking a look at what we had, what we could in the short timeline for kind of the grades that on the existing site. During a detailed design, we'll lay that out to maximize the existing footprint and site topography. So here's a high level overview. The current system is these three anaerobic lagoons, and then they basically go to the effluent storage and distribution system. So as part of the project, we're proposing, due to the high suspended solids in the incoming wastewater, a grit removal system that will help the buildup in these lagoons, making them last or be in operation longer and reduce the buildup in them, keeping the hydraulic retention time high. There's an option for additional inert solid removal after the digestion and the solids are spent. That's just asking as feature. We're working on testing with the board right now to evaluate the settleability of that material and if that warrants the treatment step in the process. The heart of the process is here in the secondary treatment process. We have pre-anoxic basins with a sequencing batch reactor, and those flows recycle back and forth between the two basins. This is where we're getting the control and reduction of the biological oxygen demand for the organics, as well as reducing the nitrogen. So we're nitrifying the ammonia, and then when we're converting the nitrate into nitrogen gas in the denitrification step here in the pre-anoxic basin.
Can we go back, I'm sorry, go back, you said it went between two basins?
Yeah.
Can you point those two?
Sure.
basins out?
So in each of these trains here, you have a pre-anoxic tank and a sequencing batch reactor tank. And so what we're doing is there's a mixing system that's by pump motive force that pulls from the first basin into the second basin. That basin then overflows back into the first basin.
Okay.
So this train, this is considered a train, these two tanks, and they recycle flow back and forth.
Okay. So you call them tanks, are they really tanks or are they?
These are the earthen lagoons.
Right. I want to jump in there because it's really innovative for an SBR to have a pre-anoxic, a segregated pre-anoxic reactor basin. And the reason we do that is that we're creating the most efficient denitrification, which is the second step of nitrogen control, by creating an environment in that first tank where you have low dissolved oxygen, high nitrate, and lots of carbon. The carbon is expressed as BOD. So I get those three ingredients, I get a high rate reaction. And I also don't have to compete for carbon in the subsequent SBR tank. So there's a nuance here with how we operate in SBR. I would say a traditional SBR, maybe 95% of them that I've ever seen have one reactor, and they just go through batches of alternating fill, air on, air off, settle, decant, take the next batch in. But those are inefficient reactors. They work, but they compete for carbon. And your ratio of your high nitrogen to your BOD is not ideal for a biological process. So we had to modify that a little bit to create a pre-anoxic SBR reactor. So that's pretty important. Luckily, there is a process out there that does this that I put in and we put in and works very well. So that's why we have a pre-anoxic reactor, but it's two aeration basins that are kind of bumped together, or two earthen basins bumped together.
So is your retention time based on digestible or based on total solids?
There's hydraulic retention time and solids retention time, and it's a function of the growth kinetics of the different bacteria that we wanna have. And so we look at both the SRT and the HRT, and we optimize between those two reactors for specific environmental conditions in time.
So can they,
It may sound complicated, but this has been figured out with the control system that optimizes that relationship.
so can the bugs take varying levels
Oh,
of?
Yep, they're fine to
Okay.
consolidate down to a lower volume or increase to a
Lower,
larger
yes.
volume. And then the fluctuation in these ponds, if you call them that, or lagoons, is maybe a couple, 3 feet. And if we're talking 27-foot water surface elevation, it's a small slice of that overall depth. And so we're batching it and managing the flow at the same time while we're controlling the environment to grow the right bacteria to do the work. The work is to reduce nitrogen.
What's the ref retention time?
The what?
The ref retention time?
About 30 hours.
Cool, okay.
Um, 20 hours is
This is upstream of the digesters?
No, this is
downstream. This
secondary.
is downstream of the digester, okay.
Yeah, so after the grid removal, we'll go into those existing anaerobic lagoons on site, the existing 3 basins. Then we will go to our secondary process.
Okay.
We've sized this system to be able to handle the flow through 3 trains, so we can bring the train online for servicing. And that can be scheduled, or if you have an emergency, you need to take the basin offline. Since this is a sequencing process, it's not a continuous effluent, we have batches that come out as those get treated, and so we have an effluent EQ basin. So that it allowed us to make the pump station a little bit smaller on the backside for transfer to the existing lagoon, effluent lagoon on site. And also gives a more consistent flow rate. We follow the solids, so that's the water flow scheme, kind of going this direction from left to right. The solids that then get produced, the biological solids that get produced here in the secondary treatment process will get wasted out. That's roughly about 0.3% solids, and so that's pretty dilute for when you consider the amount of solids that will be created with this process. And so it's efficient to then thicken that material up before you go to a potentially dewatering process. So this just reduces the hydraulic capacity required for that dewatering system, and lower the footprint and the cost of that system.
So when you said 0.3, is that the percent dry matter of the discharge, or is that the volume of the discharge?
The 0.3 would be the concentration on average in these basins, but as a system. So that would be coming here and then going through this thickening basin, we'll get to about 2%, so 0.3 up to 2%. And then the
2% dry matter,
2% dry matter.
so it's liquid still.
Correct, yeah. And then this will go into the dewatering system, we'll add a flocculation lead, a polymer, and that will get up to about 20%.
So just like running through a DAF system to float the solids out of it and then recirculate the water into the lagoons.
So a DAF doesn't necessarily, it's more of a thickening device, it's not a dewatering device. This would be like a screw press, if you're familiar with that, or like a rotary press, that'll actually produce a cake. Then there'll be a conveyance system with shaftless screw conveyors or similar.
And you'll get it to like 20 to mid-20s per
Right,
hour.
20% is, yeah, kind of like initial estimate.
So it'll still lose, but it'll be plus minus 20%.
Yeah, it'll stack, if you squeeze it, you probably get some water out of it, but it is a stackable cake.
No, so that's not a product that could be applied to land, is that the thought?
Yeah.
You're shooting at?
Yeah,
Okay, and then,
that's a traditional biosolids. What they use for municipal biosolids is somewhere between 20 and 26% dry matter. And that's what you should like, it's the same concept of like dairies, when they take the effluent out of the dairies and they remove the fiber, that's plus or minus 20%. It's just barely stackable, but you're still hauling a lot of water around. But yeah, it was in land applied.
we have neighbors downwind, would there be odor in this process? And that would be smelled in another neighboring town? And if so, where would it be in this process? Or where could it be minimized or dealt with?
Yeah. We're in the process with over the expression.
Odors can be generated in the SBRs and the anoxic basins to the most because they have a lot of surface area. That being said, it's, odor is subjective. There's foul odors, there's musty odors, manure odors, there's all kinds of odors. Generally, a well-operated wastewater treatment plant will have an earthy odor, but not an offensive odor. And Chad, I don't know if you wanna comment on that, soon on wastewater plants, but usually the headwork smell and the tail end smells. The tail end's the solids dewatering, and oftentimes if you do have ammonia, that will come out when you dewater. So you get some ammonia smell on the back end, but in general, your most volume of odor is gonna come out of your basins. You can cover them, but that's expensive, and it really has to come out somewhere. So, wastewater plants smell, but different smells.
You're not irrigating those smell down surface, which is primarily where most of our past. Okay. All smell and aspirates on that circle. That's what it was very concerned.
And maybe you wanna cover this later, but you wanna go over some of that, so basically conceptually, right? Solids handling is definitely, in the conceptual phase, we're definitely looking at other alternatives. Is now a good time?
Yeah, I think the flow sheet's good. We'll get into, we have a couple slides later to talk about solids and residuals handling, because it is a big capital cost and operations cost. And Cody will go into it later, but one of the things on this flow sheet, let's see now, is you see what we call the waste activated sludge or the waste biological solids being generated by that process. Coming into these, basically the settling ponds, then being, thickened, dewatered, and then hauled away. Another path to consider and evaluate is whether you should take the material and return it to the head of your plant and have the anaerobic digesters further digest it. This material will be volatile. It will have a higher volatile solids content, especially if you remove a lot of the inert material here or potentially here. So if I got volatile material, I can make more gas. So now ultimately, you will need to manage your solids inventory out of the system, which is the mass balance we look at. So it doesn't magically go away, but you would get further reduction in the volatile solids percentage of this waste activated sludge, which would convert into gas. That's something to consider. It depends on how you want to operate and manage your solids, whether you do it periodically or whether you do it continually. But for this level of analysis, we just assumed we would manage our own waste solids and not burden the anaerobic lagoons with the return flow. But it's a possibility, and I think you should look at it.
So the land, if it was land application, is that a different permit? Type of deal, that whole other.
So that was what that was the aha moment in the last meeting was DEQ saying, no, that if it goes through this, if it's in water, it's a DEQ permit. If it goes through the system, those removed solids are not, they're ag exempt. And so that's the stated policy today, which is, a good thing. The only thing you gotta watch for is what the consumable or what the flocculant is if you add the flocculant, then does that become a waste product? And we would just need to clarify that just to make sure.
Yeah, in terms of the WPCF permit, it would be acceptable to land apply, as he was saying, it would be considered agriculturally exempt waste, but you'd still have to meet your nitrogen loading at the field level. So whether it's fertilizer or reuse water or manure, you just quantify how much nitrogen was applied in that land application. But I think what you guys are showing me is that the solids are potentially a lot. If you are able to recycle that back to an anaerobic digester, you're managing your solids better. Hopefully have a smaller stream of waste to manage. I don't know what I call it waste, it'll be a fertilizer at that point. So yeah.
The only thing with volatile solids though, you'll make gas out of them, but it doesn't necessarily consume macronutrients. Digesters, a lot of people think like you put solids in and you digest the solid and you're taking nutrients with it. It's not the case. It will maintain a similar macronutrient loading, but you'll make gas out of it and which is potentially profitable. So I mean, it's a great idea, but it won't necessarily consume the macros.
Lisa?
I just want to let you know that Mike Hyatt and Dustin Sturger from DEQ are on the Zoom call, so if you have any questions in particular to them, they're listening to this presentation as well.
Good, thank you.
Yeah. Lisa, this is Justin Sturger. I actually did have a quick question about the system and any bypass. Does this proposal allow for or propose any type of bypass to the batch reactor system? I'm thinking of lower strength waste like data center cooling water. Would you be bypassing the treatment system for any of those lower nitrogen strength wastes?
You know, we're at a pretty conceptual level, I think. We haven't put anything on the table at this point in time. A bypass of low strength waste is certainly an option. I think Jake might have something to add.
Yeah, so what I'd add is we haven't engaged Aqua about that. We've been working on that for several years on redirecting those flows away from the digester, so it ultimately would never get to secondary treatment. So yeah, Justin, we have been looking at that as
Yeah.
alternatives. Definitely in our plan. We're actively working.
That's a really important concept, because if you're talking like 2 to 4% dry matter, you know, people think, oh, it's just a couple of percentages. But what you're handling, you're managing the solids here, right? You're managing what's in the water here. And when you go from 2 to 4% solids, it's a 50% increase in your productivity. So when you have volumes of water that don't have any inerts in it or don't have anything in, a bypass makes a ton of sense, because when you put more volume into this and you dilutes your solids, then you just have to build bigger machines to manage the same solids. And so that's why dewatering or keeping your volatile solids or your solids percent as high as possible is what's so important, because that drives your CapEx a lot lower. And so it's really important to do whatever you can to maintain those, those dry matter percentages as high as possible, because everything else you're doing, you're just hauling or handling water.
Right.
But on the reactors, because one of the things we've been talking about, one of Mark's goals is to maintain a more homogeneous discharge, to the farm. So if you're feeding variable into the secondary treatment, are you gonna adjust the retention times to then discharge homogeneous? Do you see what I'm saying?
Yeah, there'll be a steady flow out of whatever the design flow search mentioned is. The way that's managed is in these first basins. They're not only anoxic, but they're anoxic equalization. So while I'm going through a cycle of batch treatment, which is again, fill, react, settle, decant, what do I do when I'm settling in decant? I have to keep taking flow. The flow doesn't stop. So you manage that flow by accumulation in this first reactor, or this first component of this train. So this is an anoxic EQ, this is an active sequencing batch reactor. So what that does is it equalizes the input side of this equation. On the outside though, I still have a decant rate, and that's a high rate, because I have to evacuate a full batch in a shorter period of time. So it comes fast and hard. So it comes in steady, it's equalized, treated, and then I'm going, and these are taking turns discharging at a high rate. If we time this all nicely, it will work out, but you never time it perfect. So we're gonna have a 1.5 billion gallon pond on the back end to equalize each of those decant events. And then you pump out of those to the inner ponds, and ultimately you find a holding ponds.
But the decant out of the SDR is being launched this product.
It's,
Homogeneous from a nutrient standpoint, yes.
yeah,
Yeah.
each batch has got its, I mean, it could be slight variations, but they'll all achieve the similar level of treatment. So from a pounding, or a mass perspective, yeah, it's all gonna get homogenized hydraulically and from a mass loading on the.
So if you wanted to keep nutrients, if you wanted to keep more macronutrients in during farming season, like was talked about earlier, do you just reduce the retention time then to push more macros out?
There's a couple of strategies to do that. You could bypass decreased retention or SRT, hydraulic retention time, take a basin offline. You could also potentially take some of this 110 milligram per liter nitrogen, coming into the process, bypass it around, run it through a short retention time reactor just to knock down the BOD, but not nitrify or denitrify. So just take it like, we used to do 30 years ago for BOD removal on TSS. We'll let the nitrogen come back through and blend it.
So there's not an important turn down rate with these things. You don't have.
They're harder to turn down because they're slow growing. Nitrifiers grow really slow, and so
That's what I was asking.
they're not reactive. They're reactive to bad things, but they don't like to grow fast. So I would say that we can control oxygen, we can stunt their growth with decreasing the dissolved oxygen level. pH is another variable in growth kinetics. So there's some tools, but it's not it's biologically not physical.
Yeah, right. Okay, Justin, real quick, we got a question, Justin Sturd.
Yeah, this is Justin Sturger with Oregon DEQ again. I was just going to chime in on what Joe said about the solids. If when we talk about the permitting process in the WPCF for the Port of Morrow, if those solids that come out of these units are proposed to be land applied to the acreage that's under the port's permit, say the farms where they irrigate effluent water already, that's managed under the port's permit. That would be part of a review we would do in accordance with their management plan for farming activities at those sites. So we wouldn't typically require a separate permit for that. We would look at that along with our solid waste colleagues, make sure we're not authorizing land application of a regulated solid waste. But if there's acreage that this is proposed to be sent off to, or it's going to be sent off as, say, a soil amendment or agricultural commodity, that goes through both our solid waste folks and the Department of Ag. And so we can certainly put the port in touch with the right folks to get that permitted.
All right, yeah, thank you.
And I had one quick question to you guys. In terms of the effluent quality, when we're talking about 40 milligrams per liter total nitrogen, what's the ammonia and the nitrate fraction of that?
The effluent's gonna be, I would say it's mostly nitrate. We'll fully nitrify, so your ammonia component will be less than 1.
Okay. Thank you.
TN is what we're expressing as our target goal, not TIN. So it's,
Yep.
there's some recalcitrant component as well that might be coupled, I don't know these particular ways, but there'll be a small piece that's dissolved organic nitrogen.
So, but the TN represents TKN plus nitrate, right? Right.
And the TN would represent all forms of nitrogen, including recalcitrant. So
Yep.
ammonia, nitrate, and DON.
Would this process reduce the TKN?
Oh, yeah.
That's the focus.
That's the primary,
Thank you.
we're looking at ammonia, converting ammonia to nitrate, and then taking nitrate to nitrogen gas through the denitrification process, which is that first reactor optimized. Now, SPR is very flexible because we can change cell cycle times to get more anoxic time, less anoxic time, more aerobic, less aerobic. So there's lots of tools we have to optimize that treatment process to get the right level of nitrogen control, but it's, you can't pick a number and get it every day. You're gonna do better than a limit based on design, but tomorrow you can't get twice that. It doesn't react that quickly. Unless you have a major process upset.
You have a piece of equipment on a grit remover prior to, that would be a new thing prior to the digestives. And I like that you have the redundancy, you know, with the 3 and the 4th one after, but what about that? What happens if that has to go down for repair or maintenance or?
Yeah, so we're having at least two trains planned for that. With the expansion for a 3rd train, so you would have redundancy in that system. An alternative that the port can consider is because the current operation is just letting that go into the anaerobic lagoons and building up solids that for a short downtime or extended downtime, whether that's a week or something to replace equipment, that could be it could just be bypassed. So, or like if you're having 2 trains online, or sorry, you normally have 2 trains online, take one off, you're still treating some of that flow, and maybe try to push it a little bit harder, and then treat as much as you can while still bypassing some of that.
For the industry, you know, not everybody's running all the same. I know some questions Joe's asked, answered some of them, but I just want to bring it up again. Sometimes we'll have a week or 2 of downtime from one plant to the other. Does any of this is taken into consideration of how solid
Yes.
the different flows and the different?
We do a full statistical analysis of the peak day, peak hour, maximum 90%. The volatile fraction of what comes in So they're pretty detailed characterization of the influent and also the how the flow comes in or doesn't come in. For example, if you had the whole system shut down for a month, that's a problem. But 5% of the system could shut down and it's not a problem. And so we do look at that, and it's normal process control for a wastewater plant to consider all diurnal and seasonal variations in the flow and what we call the load, which is the pounds of fluids that are coming in.
And then you said, you have, I think I heard correct, 30 to 40% additional capacity. Is that taking the digesters, the whole system, or just for your secondary?
Can't speak for the digesters, but the design flow is about 30% greater than their current flow. The secondary treatment flow is about 30 size to be 30% larger than your current flows.
That's the whole concept of turning it down, is can you slow it down without killing the bugs? Is there a minimum flow that it has to operate at to keep the bugs alive?
To like speak to that, since we have so many trains that the fill up to, we can take off another train and reduce that, so, yeah.
And then you could inoculate a train with another train, you get it, start that and start back up.
Yeah, then we see that with, yeah, so honestly, we could turn it substantially down by taking trains offline if we had to go to that point.
I'm hearing a lot of this.
Yeah.
Relative to our consent. Just quick question in terms of, and again, I know this is conceptual right now, but in terms of grit removal, what were you guys thinking for that? And then second, the future inert solids, are you referring to settleable solids being like sand and grits? And if so, why would that be after the anaerobic digesters? Just because, they've presumably already been settled out, so I'm just curious.
Can you repeat the first question?
What you have planned for the grit removal in terms of, is it a basin or is it like a separator, and then?
Yeah.
And then the next piece.
Yeah, so we had a vortex and grit chain plan for the upfront.
With the rear classifier.
Yeah, okay, that's what it is.
Yeah.
Really high capacity.
Yes.
Low maintenance, right?
It's what most of the processing plants are putting the vortex machines in the front end, we're receiving, and they're working really well.
But you're not losing, you shouldn't be losing much of your organic material that you want going in.
Yeah, a washer compactor to try and clean that grid as much as possible. That's also gonna help the odors as well on that grid. It'll dry better. Inerts dry better than, or can be water a lot better than organic. So that's the approach there. On the downstream side, we're working with the port to understand the solids that are coming out of the digester, typically in a municipal flow sheet. That is where you dewater is, so normally the process, the whole flow doesn't go through anaerobic digesters first, this substantially higher organic loading. Organic loading rate on their influence, so it makes sense to do the anaerobic digesters here first. So normally in a municipal flow sheet, the spent solids are out of the digesters, it's just dead bug bodies. And maybe some inert solids that were produced from that, so. We're looking at this, does that make sense to try and just further reduce inert solids getting into the secondary process? It's something that takes up reactor volume, makes your tanks larger, you gotta use more mixing energy. You gotta clean them out more often, so those are just considerations to try and have the points of potential collection and removal of those solids identified. And then it may roll out that you do grit removal first, because that makes the most sense, so you have the digester perform after that, and then see if it warrants.
But then you're not, I see, okay, because then also, I mean, if you're able to protect those SDRs and they're not filling up with gunk. Like, inert gunk, then your maintenance cycle.
It's a huge issue, right? And to me, this stuff, there's a huge difference between total solids and volatile solids. And you do have an issue, but I tell you, I love the concept of, so because you have variable inflows into the digester, and that you can maintain, if you can recycle those, for lack of a better term, so I don't want to call them biosolids, but solids back in, and those are truly volatile solids. And you can homogenize the feedstock of the digesters and maintain the organic loading rates of those digesters and level off the gas production. That's a huge benefit for efficiency of the digesters. That would be a big deal if you could do that.
We have a question. Well, we did. Kelly from Lamb Weston, do you have questions still?
Yeah, I just was curious, and I think I heard the answer, but just want to understand again. I'm not an expert in this. So did I hear that this process is going to remove the fertilizer, so to speak, out of the water before it goes to the farm?
Flexibility.
This is saying about half of it, would be removed from the water. So you've still got a very large portion of it there, but you do have flexibility now you want to be as, nutrient limited as it was, would be hydraulically limited, previously. But you're still gonna capture that back in as a solid, and that could then be land applied.
Okay.
But yeah, I mean, you guys are losing some fraction to nitrogen gas, so about 50% of it, right, repeat.
Yeah, so the nitrogen goes out in three places. It either remains in the effluent, you have it leaving with the solids, or you're denitrifying it, turns to nitrogen gas. So those are the three ways that we get nitrogen out of the system.
But even though you're losing it, what is going out is all NH4, it's all usable. Right?
Nitrate.
Yeah. It's all usable.
Correct, yeah.
So that's a big, even though you're losing part of it,
It'll be plant based.
it's all plant milk,
Yeah.
which is, from a farming perspective is a mitigation, yes.
And then one more question I had, and maybe this is more for the port, is the intention to use this year round or only when we're filling the lagoons during the non-growing season?
Yeah, it's more likely gonna be used year round.
You'll have to use it partially year round, just to keep the system alive.
Just to keep it
Start cutting it all the way down, that's not gonna be economically viable.
Wastewater plants don't like to start up and shut down.
Yeah.
It's be very operationally expensive to do so.
What are some of the things that you're doing here that you may not have seen before, or you're doing different, or brand new technology, or thoughts?
I think the technology is pretty tried and true at this point. The only thing that's maybe a little bit novel or unique about this is employing earthen lagoons instead of, concrete bases. But as far as the process is concerned, this has been established for decades. Yeah.
So sorry to go back, but Justin, I think it's a really important concept for the process, and as we talk about OpEx and CapEx, especially OpEx. So the solids, so the discharge is gonna be gas, water, and solids. So solids that are applied on non-permitted ground, they are or are not subject to a permit.
Is that Craig? Is that who asked that question?
Yeah.
Hey, Craig. Yeah, so typically those can go through an agricultural use exemption that's managed through ODA, but that just is part of the process that would have to go through Department of Ag if it's not on the Port of Morrow's land application areas.
Okay. So we would apply for an ag
Yeah.
exemption for.
Yeah, it can be exempted from a permit. It just has to go through that process through Department of Ag and through solid waste.
Okay.
But if it's if it's land applied, sure. If it's land applied to the Port of Morrow's acreage, it falls under the port's permit, and that would be something we would regulate in terms of land application and nitrogen balance, which is what Joe was referencing as part of the plan for any irrigated acreage under the port's plan.
Okay.
Okay.
All right. One last question. Are you guys going from the top? Great. Okay. Okay, so after you got, let's say 40 milligrams per liter, or if you have nitrate, it then goes into final holding ponds, and then either it's going out to the field or it's gonna go sit in one of the 1.5 billion gallon. Totally correct, that you guys were building. So, any more nitrate lost there? We're probably gonna get some algae maybe in this week out.
Denitrification needs carbon, nitrate, and a low DO environment. So if you manage your BOD, you'll hit a point where there's no more carbon to drive denitrification, so it will stay in a nitrate form.
Okay.
And unless, Cody, you want to comment?
You have different chemical, your ponds are very deep. Yes. So you can get anoxic zones right in them. in your storage. I'm just wondering, just because, say you guys designed at 40, but we're seeing 30, I don't see. Additional nitro removal in the ponds is a bad thing, so again, okay, we're trying to preserve the nutrients as we discussed, but just, I'm wondering if there's some additional.
You might get some denitrification, some nitrogen bubbles popping out here and there, but I don't, we could model that, but I don't think you're gonna see a lot of.
Unless we added a carbon source.
Right.
And it depends on the retention time.
Which, a question, algae. Likes phosphorus, likes nitrogen, grows and it dies. That adds, that's another input to the equation.
Carbon, yeah.
That's carbon.
Yeah.
So, something to think about.
I think that's not, it's not the end of the story.
If you want to inhibit algae, then you have to remove phosphorus as well.
That was the next question, was the macros. This system is only removing nitrogen, right? The
Yes.
phosphorus and potassium loading will remain intact and exit with the water and the solids.
Yes,
Okay.
and I don't know that we even looked at phosphorus at all. You know what your internal phosphorus is? Yeah.
Any other questions on the process? So, you guys saw in the chart, the overall process flow, kind of converted that into a very conceptual, albeit, site plan, how would this lay out on the existing site? I'll let Cody and Bob kind of
Okay,
give you a tour.
I'm glad you guys spent so much time on the process flow diagram, because this makes this one easy. So, this first area of the site plan is your, influent wastewater grit removal process. And that's gonna be above ground, vortex and grit chamber with a grit classifier and a big pad to store all the washed grit. So that's step one. The wastewater will then go into your anaerobic ponds, your digesters, to have that first step of treatment. From there, it will be pumped over to this process here, which is what we're calling to the advanced secondary biological nutrient removal process. So as it's pumped, it will come to what we call a splitter box, which will separate that flow into 4 equal flow streams. It will then be treated in 4 trains. As I mentioned, or we mentioned earlier, each train will consist of a anoxic equalization basin, followed by a sequencing batch reactor basin. You can see the little line inside of there, that's the bottom of the basin. The line on top is the top of burn. They're about 30 feet deep, 1.5 to 1 slopes, stabilized, lined. We're discussing different construction methodologies and anchoring methodologies for the equipment. But it's essentially one train with 2 basins. The first is anoxic, second is true SBR, and there's an internal, what we call an internal recycle. And that internal recycle takes the nitrified suspended solids and returns them to this anoxic reactor for a higher rate nitrogen removal process. So it's an efficient process, to say the least. The total volume here is 22 million gallons. So if you want to know your HRT, 22 over 13. Right, I got attention time, and we'll convert it out to hours. So that's the overall secondary treatment process. A couple of features, and some of the challenges. We'll get to it here in a little bit, with earthen basins, because there are challenges with how we actually do this work. A flow sheet's fine, but how to physically make it function is important, because the operators aren't gonna be happy if their basins don't vent, so you can't get the oxygen transfer, or the pumps are hard to maintain, the blowers are difficult. There's lots of nuances putting this into an earthen basin. It saves a lot of money for concrete, but there is some challenges. I'll walk through that, and then we'll go into some of those challenges and how we think we can solve them, how we know we can solve them. So you have your 4 trains, each will treat about a quarter of the flow, slightly oversized, so you can take 1 train down. They decant into this 1.5 million gallon equalization decant holding, again, an earthen pond. And there's a small pump station here that will deliver it to the final storage. On the solid side of things, we'll take solids generated by this process and bring it over to 2 more settling ponds where we concentrate that 0.3% concentration to about 2%. These are also alternating settling tanks. They're like clarifiers, but they're simple clarifiers, very simple clarifiers with no mechanism, just pretty much a cone shape with a big sump. We'll use a progressing rotary low pump to pull this out and run it through machines that thicken it to 20% kick. Or deliver it back to the anaerobic lagoons if you choose that if that makes sense. So this is your process. If you do a circle here, it's about 20 acres, to give you a perspective on footprint. Total volume is 22 million gallons of reactor volume. If you needed to, this note number 2, this was the additional solid settling bases if we want to further polish off some of that inert material. Any questions on the site plan?
Are they scalable? So it looks like you got trains or lines. So you have reactors that are hooked, maybe that's just like a common pump house.
Yeah.
But are they,
Over here
yeah,
is the MCC room, the electrical room. So we got,
but it serves two blocks, serves 2 trains. Correct. So is it scalable? I mean, can you add?
Yep.
Can you add 1 train or take one? Can you build 2 trains and then build more?
you
Or is
could
there?
build, in fact, you got one sketched in here, note number 12.
Cool.
And the other thing I'll note, this is a concept. We laid this out based on topography, or what made sense from a cut fill balance.
Cool.
But this could be reoriented on the site if you had other space planning needs that you wanted to look at a 20 MGD ultimate build out. We could.
So you could build headers for your common areas and bolt on
Yep.
as you grew or whatever. All right.
There's phasing that's always considered,
Right.
and you can see you could do that. But yeah, this little building here, would house the blowers. There's a pump station there as well. There's a MCC electrical room.
Okay.
And we'll go through what this looks like physically just in a bit. Next
You
slide.
haven't talked about the grid, like where does it go and what, is there permits required for
The
that?
grid's gonna go on this big pad. The building is actually small, but the grid removal is the small side of it. Yeah. Right? Yeah, sure. This pad right here is gonna be big piles of sandy looking material. And that would have to get picked up with a loader and properly managed. What does that mean? That's a conversation we'll have to have. You know, well, how's it classified? Can it be used as a fill material on site? But it's gonna be a sandy type, washed sandy material.
A lot of them, if it's coming out, what I've seen is if it's coming out of a reuse stream, they'll put like bottled water to do the final wash in a vortex, and then it's just sand, and they haul it back to fields. But if you don't do some sort of bottled water, then it's got, in theory, it's got a reuse stream in it. And so then it has to be land applied with the regular, with the other solids, is what we've seen in some of the plants.
So
But
that,
it's not, it's fine, it's knowable. It's actually preferred because it's a higher percent dry matter, it's heavier, so you're not having a lot of water or.
so a couple of things we want to just hit on. We did look at a continuous flow process. We couldn't resist. You know, if we have to look at traditional treatment processes in earthen basins to see if that was gonna work better. So we did evaluate a continuous flow. AS stands for activated sludge, which is nothing more than concentrating biomass and retaining it. So we can do more work in a smaller reactor size. BNR stands for biological nutrient removal. We got a couple proposals for that technology and equipment, and they were more money. We're waiting on a couple more, but that is a proven process to remove nitrogen. That's what the majority of municipal wastewater plants are designed around, is a continuous flow activated sludge process. They need clarifiers, and clarifiers have mechanical mechanisms. They have pumps that return those solids to the front to maintain the biomass, so they tend to be a little more money. An SDR or a batch process does all the work in one basin, and it treats it in batches, then your reactor and your clarifier are combined. So we looked at those. And that's what was ultimately what we think is the best choice. The other thing which triggered this whole conversation about upfront grid removal and settling is that your influent had a very low volatile component. If you look at our total suspended solids, there was a lot of inert material. And that's what led us to say, let's try to get that out up front. Let's not carry that through the process, consume volume in your anaerobic reactors, or have to move it, pump it, it's dead weight. So that was the indicator based on the good data that Jake and his team provided, that popped out at us. So the process is clean. We have a good flow sheet. The challenge is how do we do it in an earthen basin? Concrete's typical because it's a very nice geometry to mix and aerate. Earthen basins are harder because these slopes and mixing energy kind of just gets lost on the side slopes.
These are open top basins?
These are open top.
Oh, fascinating, okay.
So this is a 2.4 million gallon basin. It's not as deep. So this is about 2/3 the depth of what we would suggest for you guys. But this was a photo of a leachate treatment system up in Alaska.
Did you factor in fusion dust for the open?
What?
Did you factor in fusion dust for the open?
No.
No, we didn't.
Might be worth looking at a second.
Something that we gotta look into, I definitely enjoy it. It's very interesting.
We don't allow it.
Greg, say that again. What did you call that?
Fugitive dust, just blowing dust.
Okay.
Usually. That's an air permit term, sorry.
Okay.
Escape from penitentiary.
Yeah. Exactly.
Plant a lot of grass around.
Well, these are fields for you.
So this is a earthen lined lagoon with a concrete bottom. And this here is what we call this is a jet aeration system. So it's a jet header. We'll talk about more about that and why we chose that as your aeration and mixing device. We looked at prop mixers, big bubble mixers, floating mixers. There's lots of ways to mix up a lagoon. They all have a horsepower requirement. They all have advantages and disadvantages. There's also lots of ways to aerate a big lagoon through the surface, from the bottom. There's lots of considerations. Ultimately, we settled in on what we call jet aeration, which is, in a simplified analogy, like a hot tub. You have a pump that circulates fluid through a nozzle. That nozzle has a venturi, which is an inner nozzle inside of an outer nozzle. The venturi creates a vacuum, and in your hot tub, it just draws, it sucks in air and makes the bubbles. We'll supplement that with blowers, compressors. We have to pick the right compressor that can handle the hydrostatic head on top of that bubble release. So if we're looking at a 27-foot depth, we have to have, 12 PSI compressor to get that bubble to go through that water column, plus the losses in the line. Jets give a little bit of assist because of that venturi, and they can also separate mixing from aeration, which is a huge advantage for a biological process, because I can turn the air off and still mix by continuing to circulate the fluid. So I can go into what's called the anoxic mix sub-cycle, which is a biological condition that will promote denitrification. In this case, it's the completion of the nitrogen removal cycle. O&M is a big deal too. It's the last one, could be the first one, but what do you do if you have to get in this basin? What's gonna break? We looked at fine bubble diffusers, which are standard in the industry, but every 7 years, you gotta go replace the disc. It's a 9-inch membrane disc that has a ring around it. You gotta spin it off and put a new one on. In this case, it would completely fill the floor of that basin. So there's a big manpower need to go in there and take those off, put them on. And you have to drain the basin. I would argue that, we argue that this jet system, there's no moving part other than a stainless steel jet. So unless a bolt shakes loose, you should not be in that basin, unless it's to clean it because you didn't do a good job on your cleaner and solids removal.
Are you using that continuous for the process, or are you using that just to agitate the fluid before decanting?
It's integrated into the SBR, and so the control panel for the SBR will sequence through fill, react. During settle and decant, the pumps and the blowers are quiet. Quiet and settling, and then the decanting of that effluent. So a certain part of every day, you are resting in terms of the mechanical energy and aeration you're putting into the basins. Next slide.
Good question here.
So what was your choice? Why was your choice going for the earthen dams and the concrete dams, if the concrete dams, or the dams, side up boards or whatever you wanna call them? What was the, yeah,
Cost.
That's if they're a lot less cheaper, they're a lot less, they're cheaper built. Sorry, that was fortunate.
so what would be the, what would be the lifespan of the fabric lined? It, or the concrete?
It really depends on how well it is taken care of, you know, the hardest thing on liner is UV, sunlight. Under, you know, constant exposure, these liner systems will have maybe a 20 to 30 year lifespan, just from sunlight. But all it takes is somebody to put their back tire through it to rip it in a day, so.
But you'll have, but these are, I mean, they're a 20+ year life if taken care of at least, and you'll have monitoring. So they'll have a lot of times when they're putting lagoons in with HDPE liners, they'll have monitoring devices. You'll put gravel around it, and then you'll have monitoring tubes down the side. You'll have upgrading and downgraded monitoring wells.
Correct.
I mean, you catch leaks on HDPE stuff.
There will be,
It's the same with concrete. If a concrete tank isn't stressed right or cracks, or you get some sort of settling, I mean, it's, you have equal risks. This is just about a third of the cost.
so to give you some perspective, you know, the port has some lagoons that have been in place for, what's the pond 41, 30 years old?
2011.
Oh, it's not that old.
That was not.
Okay. Well, there was concrete before then, but it wasn't mine.
Sure.
Okay.
Location.
Well, I have experience working with other clients and other projects where we have, you know, very similar HDPE liner systems that have been in place for 40 years, and they're just fine. They tend to get more rigid over time, they're not as flexible, but as long as you're careful about, you know, moving equipment around and, you know, doing your normal O&M routines, they will last for several decades. However, you do need to plan on eventual replacement of that liner system.
Yes, quick question on that, so I mean, you guys were providing redundancy, so you can't take one offline too.
So that's right. Yeah.
Is there kind of like a freeze thaw cycle, is there an issue with having a lagoon where you're every day filling it empty, fill empty, or like, less like would be more just about
Right,
line extension?
you're only moving about a foot or two.
Oh, that's right, that's right,
Yeah,
that's
We're
right.
not filling top to
The thermal
bottom.
mass is there, and I would further
Yep.
say, if you get into UV, it's gonna be over on top where your anchor trenches.
Yep.
Then you could go back in later, repair that section, overlay that section, you can have sacrificial, you know, layer at that top 5 feet if you wanted to. But underneath the water, you're not gonna see the same degradation you do right along top of our.
Yeah, okay. And when you have infrastructure in the bottom of a lagoon like that, that really mitigates any potential bubbling or stuff like that. I mean, so you'll have, with that infrastructure in there, that'll be a really high, really.
So
liner.
we looked at concrete bottoms, because it's an easier concrete to place and reinforce. It's 8 inches. It's not like a double mat, thick concrete wall, it's gotta withstand a lot of hydrostatic force. It's not a wall, so this is cheap concrete compared to a tall wall. That's something we're evaluating, we're looking at different ways to value engineer this. You do need supports for these headers. Let's go to the next slide, if it might be a better picture. Now, I think I kind of hit there you go. So there's a picture of a nozzle. This part is the air, this is the fluid. At the very end, they have a submersible pump at the end of the header. We don't have that in our design, we have a submersible pump, but it's accessible off a guide rail system and a crane. So you just pull it up. This one, in my opinion, having it hanging out in the middle of the pond was not a good idea.
So are you decanting through these and then filling on top?
No, we have a separate decanter. It's a what we call a solids excluding decanter. So it's a weir and it's got a little internal mechanism that keeps the solids from migrating out, and it's got an airlock and a release valve. So it's a fixed weir, and then you open a valve, break the airlock, and it withdraws the prescribed amount to what we call bottom water level. Top water level is full, bottom water level is the bottom of the batch. When it hits that, closes the valve, control panel says, okay, I'm back in business, we start filling it. And so it goes through that iterative cycle or that repetitive cycle. So this is a jet header. We like them because they make they have a high transfer efficiency because there's a lot of turbulence. Wastewater, sometimes there's an ideal oxygen transfer, and then there's a not so ideal. And depending on the biological process, the amount of surfactants, the age of the biology, there's an alpha factor, they call it. And jets have a high alpha, which means they're more efficient than a fine bubble. And they kind of equalize out in terms of the overall efficiency per depth. But that's why we pick jets, is because they have independent mixing in air. They end up being pretty cost competitive and simple. There's not a lot of maintenance. And there's lots of jets out there, lots of generation, especially in industrial wastewater treatment. Next slide. Here's just another view. You can see the airline, two headers. This wasn't a rectangular base bottom in this lagoon. We would propose three headers and bi-directional headers. So this is just an example to give you a perspective on a 2.4 million gallon lagoon.
One thing to note on this design is kind of similar to your concerns related to frost thaw cycles is, you know, these airlines, they'll be vibrating. And we're concerned about that interface with the liner system. So if you look closely, the airlines are actually installed on concrete ramps that go up to the top. And then the line then terminates in the concrete ramp. So that's another thing that we would, you know, suggest as kind of a value added item. It's a little bit of upfront cost, but it's gonna buy life without liner system.
What kind of security around all of this have?
As of right now, we would plan on, the whole site would be, circumscribed in a 6 foot tall plus chain link fence with some barbed wire, similar to the port's existing facilities. We could certainly explore other avenues for security, but, as of right now, that's what we're planning on.
This is the air pattern as they were filling that particular lagoon. This is a residual. It's got all the fine details of the layout. But kind of I'm gonna hand this back to Cody. He's gonna talk about solids more. And that's, you guys keyed in on that. I think it's worth talking about even further.
So if we look at the solids handling, we mainly have two sources of salt. You have the inert solids that come in with the process and the biologically produced bug bodies. Another way to look at it, the waste activated sludge. So just to quantify what inert solids loading could be coming in, and you could be at the design conditions of 13 MPDs, you're looking at close to 110 dry tons a day, 128 cubic yards of material a day that would be at this time just building up in those anaerobic lagoons. So that takes up a lot of volume. That then is arguably more expensive per pound when you have to roll that cover back off and remove all that material out of there. We have a grid system, it's removed. You don't need to add polymer to remove it. It's a cheap pound of solid removed from the system and protects downstream equipment from erosion, wear and tear, and it's not going to build up in other basins. So if you fill up your anaerobic lagoons, you have more carryover into your secondary process. Since start filling up secondary process, you're gonna have more downtime and maintenance there. The inert solids dewater and compact, they have higher density than the biological solids. Biological solids are like a fluffy brownie. It's a material that only is about 20% dry, and it takes up a lot of volume.
Yeah.
Floating ground.
Floating ground.
Okay.
Wet stop, provide better term for it, but the biological solids. While you are dewatering to about 20%, they still are, they're pretty light, they have a lot of water still in them. And so from a cubic yard volume. Even though the dry tons are a fraction of the incoming grit, still is actually more volume they have to manage and deal with either internally to the process or hauling outside. We kind of talked about the solids, ways to manage the solids. Right now, we're thinking of a vortex and grit chamber for the grit, polymer dewatering system, for the biological solids after the thickening process. That would either be a screw press or a rotary press. Those are low speed units that we see less wear with them, and we see that we get more consistent product out of them compared to say like a centrifuge. They can be temperamental, and with the high speeds, when it goes, it goes. And you gotta have backup units in rotation. Screw presses, rotary presses are typically able to be serviced on site by the operations staff. And what's nice about both the screw press and rotary press is you'll have trains of that unit process, but there may be 4 screws on one train or 8 rotary presses on one train. So you can take a unit out of service and only lose a fraction of your capacity and keep the other ones in operation.
I got a question on inner solids there. From the influent wastewater is 128 cubic yards a day.
Yes.
It's a lot. That's a
dump truck-
a dump truck's 10.
That's 12 and a half trucks a day.
Yeah, that looks like a lot.
That's where our strong recommendation comes from to consider grit removal.
Gotcha.
And these are projected at the 13 MPP, so just to put that in perspective. But yeah, the influent solids are roughly 90 to 95% inert.
It would drastically reduce our long-term operational costs. As of right now, we've been budgeting for removal of digester covers between 7 and 10 years of operation. So this would extend those maintenance times drastically.
Right. I mean, it sounds like this is something you guys are trying to do before the rest of the project and stuff, right?
Well,
I'm not suggesting that, I'm just, we're looking at 95%.
when I look at that number up there, 12 dump trucks a day, and you said in the digester. After a year, your digester's gonna be full. At 12 trucks a day.
So I would say through the digesters currently, what percentage carries through the digesters?
You have about 20% of that carrying through. So the digesters, you're removing
Oh,
about
you got
80% of that.
8.5 trucks.
Yeah.
Yeah.
It's still a lot. Okay. A lot of accumulation is happening at digest.
And to put it in perspective, your average annual day flow is like 6.7 MGD currently. Max month is about 9, and then so our max month here is 13. So just to kind of put that a little bit in perspective for what you're seeing today.
So Jake, because they quantified the actual accumulation rate in those digesters, and that's where the 6 to 7 year cycle comes from, because, all these are based on peak numbers, which rarely happen.
So here's just a schematic of a vortex and grit chamber. You have the material coming in, there may be an assist of a aerated jet or something or a paddle to promote the vortex here. And then typically the in and the out actually are right next to each other. So you have the full distance around here, the grids, due to density difference, gets pushed out to the edge and then settles down as it continues here. So that this doesn't plug up down here to come like air lift, so that fluidizes the grid so that can be removed from the system. So that'll go to like a grid classifier, that then you bring in additional water to wash the organics out of what gets separated here. The organics are returned to the process and the grit will be stored, stacked on a bed. So the main benefits, going back to considerations, that low volatile to
total suspended solid ratio of the influent drives the decision to look at a grit removal system. And you are removing about 80% of the solids right now in the main aerobic digesters. So reducing the accumulation in those digesters, reducing downstream pump wear and erosion. These solids are removed without a flocculant aid, and so that's cheap solids to be removed from the system. The inert solids that do get passed on through both the digester and secondary process take up volume. You gotta mix them, you have to account for that in the sizing, so if we are going to design for a higher inert loading in the downstream processes, basins get bigger, mixers get bigger. All those systems will need to be bigger, so that is a way to reduce the sizing of that secondary process. Then just some disposal considerations is if it is allowed to do on-site disposal or there's the landfill option versus those solids. The way we would approach this in the detailed design phase is we would characterize the grit, so we would do like a particle size distribution or a mesh study to see what is the gradation of that material. Then we would share that with the vendors and then design and select the best system to remove the highest removal efficiency for your specific wastewater. Then on the biologically produced solid or waste activated sludge, again, the reactors or the basins will have about a 0.3% solids concentration. The thickening cells will thicken that up to about 2%, and then dewatering it with flocculant aid, that polymer will get you up to about 20%. So if you look at it from 0.3% all the way up to 20%, that's a significant reduction in volume and just how typically you manage waste activated sludge. Again, there is a way or an option to recycle this back into the digesters, produce more biogas that will further reduce the amount of solids to be managed. But in that system, you will have some more deposition inside the head.
I'm sorry, did you give volumes on the solids discharge?
Yes, on the first.
Yeah, correct. How did he get up there?
So here on this slide, we just summarized the biological solids production from the facility, and the inert solids that is coming in with the wastewater.
And this is at peak flows of 13 MD,
Yeah.
which you guys currently do not have, so this is much higher, well, 35% or so higher than what you're seeing during today's peak events.
Yeah. So we size our equipment to make sure we can handle that max days so that you guys have the capacity and redundancy to meet that demand.
That slide is a great example. It's a great illustration of the expense of hauling water around. I appreciate the fact that you guys showed the dry tons versus as applied tons, because it's, what was it, 20% of the dry tons, but more volume.
Correct. Yeah, lower density and higher water content.
So we've come up with a very preliminary cost estimate to match this conceptual system that we've been talking about. We've broken that cost estimate into several different categories, which we'll share in the following slide, but I want to review what's included in these various categories. So site work includes, excavation, mass earthwork, concrete, if we are going to go with those concrete floors that we saw earlier, piping for the basins that you saw in those photos. That includes slope stabilization efforts for the edges of the ponds. That's again with the assumption that we're not going to encounter any groundwater. And we've got a potable water supply from our Swanson Road, which actually is already on site, based on what Jake told me earlier today. The equipment section includes, blowers, pumps, decanters, the grit removal system, aeration and mixing, our dewatering system, plus redundancy added to all of those items. Any shelf spares that we might recommend you guys have on site. There's a building line item that is really just the shells that contain this equipment. So these are assumed to be, you know, concrete slabs with pre-engineered metal buildings. Pretty simple structures. Electrical instrumentation and controls, that covers everything from power supply to the site from Umatilla, all the way down to the control wiring, the PLC panels. Those are the computers that kind of run everything. Then we have soft costs, which are, you know, contractors, overhead and profits, detailed engineering, construction management, and any QA/QC services performed on site during construction, whether that's related to the liner system, the geotechnical aspects of the project to ensure, you know, compaction is being achieved prior to liner being installed, for instance. And we also have some minor planning costs in there that we threw in for various miscellaneous items. Finally, we do have a healthy contingency at this point of 30%. As I mentioned, this is about 4 weeks of work, and I anticipate a detailed design of this system will take somewhere between 9 and 12 months. So we do reserve a very, very healthy contingency, and that number will get whittled down over time. So with that all said, we'll share the big numbers for you. We're at a total cost of about $71.5 million right now. But, you know, bear in mind that 30% contingency, that's $13.5 million today. All of these costs are based on project experience that we have. We have projects between Southern California and upstate New York. We kind of aggregate all of that experience and we put it into a big spreadsheet here. I realized that, you know, some of the costs that we included here might be from Southern California, which tends to be a bit higher. Some of it might be from, you know, Iowa, which might be lower. So this is very, very conceptual level cost estimate, and it will get further and further refined. I'm going to be working closely with Jake and his team. He's got a very good understanding of the labor markets around here. I think equipment costs are what they are. It doesn't matter where you are in the country, lower costs or lower costs, but the big variability that you do see tends to be with labor and what we call general conditions. That's kind of where the contractor makes their money. So we've got a site work of roughly $10 million or 9.3 million, equipment costs of 14.8. Buildings are at 6 million. Electrical is 14.5. Again, our contingency is just about 13.5. The soft costs are 11. That gives us a total of just under $70 million. Now we've got two kind of value-added items that we've talked about to an extent today. But the first being the concrete floors of the basins. That's about $1 million. And then the second is the primary settlement, which is another $1 million. So, you know, $2 million in what we consider to be, you know, value-added items that we would strongly recommend you guys consider. I think over the life cycle of this project, you're going to get that $2 million back for sure. So you got to consider the life cycle costs of this project. You know, there's O&Ms that will O&M costs that you'll be paying for the duration of these facilities. So,
But this is so the 70 million is that for the 4 trains, which includes 40% growth capacity?
yes, that is
Okay.
13 million gallon per day system.
Okay, so if you divided that by 4 trains and added maybe 10%, I mean, if you backed a train off, then would it just be correspondingly or linearly less?
Yeah, add 10-15%. That sounds right. You know, divide by 4, add 10-15%. I think that's a reasonable way to break it down.
Okay. So you could treat 100% of the volume today for less than 50 million.
Yes.
Okay.
But with no growth?
Correct.
Right, okay.
Right, but the growth if it's stageable, if it's scalable, then you just bolt on another line or another train.
You know, we have to look very carefully at that. We still want to program a certain level of redundancy into the system for both planned
Got you.
and unplanned maintenance. So,
Got you.
you know, it's not so simple as just dividing by 4 and adding 15%. We would look at it a little bit more closely and maybe suggest a slightly different configuration, but speaking
Yeah,
in
this-
generalities, yeah, you're right.
Got it. I mean, and this is just FEL1, right? I mean, this is just feasibility level stuff, so appreciate that.
That's right. That's right. So. That's where we're at. It's not a small number, but it's not $150 million either.
What does the operating cost do? You went from 40 parts per million up to 7. Does that change it much?
It really doesn't. I think it's, you know, it's gonna be Chad and his guys turning levers and, you know, changing valves and stuff like that. And I think,
And then the variation and stuff still have, the lowers are running, so you can slightly reduce the cost, but nothing to top about.
yeah, it's nothing significant though.
But to go from 40 to 30 would take a lot more residents' time, so maybe potentially another.
Probably talking larger lagoons, maybe another train. I don't know if we can do another train, but it'll certainly get larger.
So compared, yeah, so I guess 2 questions there. Compared to the other system, Jacob, that you guys looked at, do we have apples to apples on yearly operating costs? Because it's a lot less expensive.
I would say it's apples to apples, yeah.
Oh, okay. I mean, so similar operating costs, but different capital costs.
This would most likely be probably a little higher labor intensive, but less from a chemical and energy consumption perspective.
SBR compared to the house system.
In my opinion, it's
So-
worker.
Do you have feasibility level operating costs for it, or do you not have an OpEx slide?
We have not gotten to operating costs quite yet.
Okay.
And then second question was just, so let's say, I like the idea that you guys talked about being scalable in some sense, right? You can add trains potentially. But what if, for example, 10 years from now, we say, well, the port actually needs to go from 40 down to 20? You know, again, everyone knows there's big discussion on what an actual number should be, but is this compatible with some other add-on or technology down the road that you might like to try
We have to add technology, we have to add volume.
Right.
So we're operating facilities like this that are getting total nitrogens of 6 at 5.
Oh, okay.
So the process can be configured to drive nitrogen very low. As I said before, it's a function of the solid residence time
Yes.
and the hydraulic resident time to do the work. So, for example, if you said we need to drop it another 20%, as your fifth basin, don't change your flow. Just lower your treatment standard by 20%. So it all comes down to how much aeration volume you have, how much anoxic volume you have, and it really is not even about volume, it's about mass. Mass of biology under aeration or under anoxic conditions. And how quickly can that bacteria convert nitrogen?
So you said we don't need another technology.
Correct.
Yeah.
Yeah.
Yeah, so I was just,
It's scalable not only in flow, but in terms of its performance.
yeah, so that, I think that's really important, and I think that's part of what we were discussing last time, is what you guys are describing. That ability to operate it differently, to get different, whether lower or higher treatment targets for nitrogen, I think. Gives me a lot more confidence that long term, the port can adjust to whatever the challenges are 5-10 years from now, so.
Yes.
As we go through design, we'll talk about redundancy, we'll talk about safety factors. There's other terms about reliability and consistency. Consider you got a 1.6 billion gallon pond.
Yeah.
That's not the same as dropping it in a trout stream where you're gonna kill the fish the next day. So if we did 30 milligrams per liter, because the operations staff dialed this thing in, you did that for 300 days a year. Theoretically, for 65, you could have a higher concentration and you all blend out. It's in the big pond. We don't, so as we design things, we have to calibrate with you guys on How, does it have to be 40 milligrams per liter every day? Every week, every month, every year, there's annual averages. Most municipal permits are written around the 30-day average. Sometimes they have a 7-day average. But a 30-day average means you could have a bad day and a good day and they cancel. So that's different than an instantaneous limit of you can't ever exceed 40. So that's calibration with you guys on, you know, where your safety factors live.
That's right, yeah, thanks.
And at this level, we're conservative, I can tell you that much.
Maybe just to expand on that point just a little bit, as you were talking about getting to really low nitrogen levels, there's other operational costs, I mean, because you need carbon to deactify, and so you may be looking at bypassing some around the ADs, which could impact biogas production, or you're sourcing an external carbon source, so those are just some things that
Yeah.
you're modifying and giving it the conditions it needs to make sure that you can work them.
Yeah, yeah, I think what I'm hearing, which is very important, is the intrinsic nature of the process, the chemical, biological process and infrastructure itself can be managed in different ways to hit certain goals. And so if you spend now 72 million rather than 150 million now, it sounds like the team would be able to adapt to some different scenarios or challenges when you're managing six different farms and different needs from everyone. So that is just the operational flexibility of our problem technology rather than the uncertainty that I think personally I was feeling with some of the other setups with the reassuring.
And really the cost reduction from 150 to 72 isn't necessarily a fair comparison. Because the 150 was a hard construction cost, right? This includes saw cost and a 30% contingency. So if you want to compare hard cost, you're talking 150 to.
I think it was 56, 57, something like that. And strip out the contingency and the soft costs.
Yeah, I think the contingency is very fair at this point because there's a lot of technical utility.
So when it goes out to the farmer's fields, is it gonna be consistent?
Yes.
Or is it going to
That's
be?
the idea.
The equalization basin first, that combines the four or five different trains into one. But then from there, then you've got the pond 41, recycled water pond where it's gonna mix. It's gonna have retention time there, and then you've got 1.6 billion gallon ponds as well. So I mean, when you're producing water today, that's not actually hitting the field until next year. Right?
So that wouldn't be accurate. You produce it today. Why wouldn't it hit the field next week?
It's hitting that big pond.
Yeah, but you're not holding the pond full in the summer.
We gotta get rid of that water today.
Yeah, constantly.
So when you shut down for the winter time, you're gonna be filling those ponds, and you arguably aren't gonna start March 1st because of soil moistures and temperatures and other stuff that comes out of it, and you're gonna have problems at the end of the year. Take your 244 day irrigation period, you really have 150 days of irrigation, so you're running a 20 million gallon system to get all that water out in time. So hence you store it, you're going to keep it in that big pond for a lot longer thing.
But you're right, some of the water today was pretty high.
Yes.
That's why regulated dilution water is very tough. You gotta, I mean, the higher you can keep the concentration, the less volume you have to manage and store. So if they're gonna regulate, if the water that comes out of the data centers is regulated exactly the same way, diluting it and reducing the solids just makes it so you have to handle more volume. It's tough. Because you have to size everything. You have to size all of the infrastructure, primary and secondary and application fields to handle volume with lower concentration of solids. And adds a lot of cost.
Any other questions?
No, thank you.
Yeah.
Well, no, maybe not a question, but I think, you know, and I don't know what the port's, you know, deliverable is. Obviously, it's the reduced CapEx is certainly intuitively seems to be a huge thing, but you really got to understand the OpEx, especially when you're talking about, you know, hundreds of truckloads a week of solids that need applied. You know, the OpEx is, you know, that's just really got to be the next. Hopefully that is the next deliverable, and the port's able to do that. Be great. It's great work otherwise.
Yeah, I think one, just a consideration for that, if it's not getting removed up front, it will need to get removed from basins, and so it's that pound is still there, it's just, do you wanna deal with it continuously or on a periodic basis? I can also swing how you budget and look at OpEx too as well. Is this a big future cost, or are we trying to manage it on a daily basis?
Yeah, I prefer to take it front end.
Yeah.
Or consistently,
It's a great point. You have to look at OpEx maintaining a clean system, not you got, if you are going to do a settling pond that's going to only need to be cleaned periodically. I mean, that you have to include, even if it's every third year or whatever, you have to amortize those costs out too.
It was important to me to have some adaptability, like the point you were addressing was important to me, because if further regulation comes down the road where we have to adapt and take more out, we can. The value of the nitrogen in the water to the farmers is important to me as well. Symbiosis, instead of just going in and adding it later. The decreased capital costs and strain on our industry is important to me as well. So I'm encouraged to hear this presentation today versus the one that we heard before. Honestly, I want to treat it down to 7, and if we needed to dial it up, we could, or if people wanted us to, we could. Not to say that we can do that, you know, instantly with one dial here, but we could, should the issue arise in the future. It sounds like to me, if I'm off base, please tell me. But,
All right, any other questions for anybody else? Okay. Thank you again.
yeah, thank you for having me.
We'll adjourn our workshop 3:16.